All right, let's get started. Today we're going to be looking at the spectral theorem and a little bit on outer products and a lot of linear algebra today. So let's take a quick recap of what we've been doing so far. And I think starting like Monday's discussion, we started to look a lot more into linear algebra and a little bit of, I guess, machine learning. And I think we're moving on to a new module now where the main focus is to use linear algebra and machine learning to kind of understand like how certain systems behave in the real world. And we're gonna like take all these like concepts and ideas and apply them to actual like control systems, but also to other applications as well. So like last time we saw system identification, which is a way to use least squares to identify an unknown state space model. And in lecture, we took a look at the singular value decomposition, which is a way to break down a matrix as a sum of a bunch of its features. And I think Mickey went over all of the flag examples, and I have a very similar example here where we just have an image here and we're breaking it up into all of its singular values. And the more singular values we add up, the more like, I guess, closer we get to the actual image. But I guess you might ask what the singular value decomposition is. And the singular value decomposition, as I kind of stated earlier, is just a way to break up a matrix into a bunch of features and a bunch of like, I guess, important features of the matrix. So the SVD as a whole, we're not going to be talking too much about it today. We're going to be building up a little bit more of the linear algebra fundamentals to build up to the SVD, but the SVD has a lot of applications in things like image processing, kind of how we saw with the flag examples, machine learning, kind of define like, I guess, the most important directions of your data, and also in controls. And in controls specifically with state space models, we'll see an example in the next couple of weeks where you can essentially reach a desired target, similar to what we did for controllability, but we can do this with minimum energy using the SVD. So the SVD, in essence, is just like, I guess, a special type of linear algebra tool, sometimes referred to as the Swiss Army knife of linear algebra. And it has a lot of applications, as we'll see in the next couple of weeks. And today we'll just be looking at the very, I guess, fundamental linear algebra concepts to build up to it. So let's actually dive into some material now. So the first couple of things I'll talk about should be reviewed from 16A or Math 54, but that was probably a long time ago. So it's always good to go back and review things. So let's talk about inner products. So inner products are a way to multiply two vectors and output a scalar. So usually our vector space V is Rn, and our vectors x and y will be vectors in Rn. And inner products are a way to define multiplication. So one way to multiply these vectors is just to take the transpose of x and multiply it by y. And this, if you look at the dimensions, well, x transpose y, this is going to be, since I guess x is a length n vector, x transpose is going to be a 1 by n, y is going to be an n by 1. So if we multiply this, we're going to get a 1 by 1. So the inner product is going to be a real value, or just a scalar in the reals. And inner products, like multiplication of vectors, let us define the norm of a vector. And the norm of a vector geometrically kind of tells us like how big a vector is, or it tells us like the size of a vector. And we do this by defining the norm of x as the square root of x transpose x. And more commonly, you might see that the norm of x squared is equal to x transpose x, or the inner product of x with itself. So any questions about inner products and norms? I know one common question students have asked is, what is the difference between an inner product and a dot product? And the dot product is just a special case of the inner product. So this inner product here, x transpose y, is actually the dot product. But there are other ways to multiply vectors that we're not going to really look at it in this class, but we could also say that x transpose y is in fact equal to x transpose A times Y, where A is a matrix. So this is just another way to define an inner product. Some other inner product. Okay, and if we don't have any questions, let's talk about orthogonality. So we say that two vectors, u and v, are orthogonal if their inner product is 0. In other words, if the inner product of u and v is equal to 0, the vectors are orthogonal. And to kind of give some geometric intuition behind what this all means, you might remember that the inner product of a vector, we can define the inner product through the definition through cosines and norms, where the inner product of u and v is equal to the norm of u times the norm of v times the cosine between the two vectors. For example, if we were to just draw out two vectors, like u and v, then the cosine between the angle between the two vectors, if we were to draw them geometrically. And if the inner product between these two vectors is equal to 0, then since these vectors will always have positive length, this tells us that the cosine of theta is equal to 0. And we can say that the angle between the two vectors is equal to pi over 2, or 90 degrees. So in other words, if you draw these vectors geometrically, they're going to form a 90-degree right angle. And to extend the definition or notion of orthogonality, we can say a set of vectors, u1 through un, are orthonormal if all of the vectors are mutually orthogonal and have norm 1. And what this means is the inner product of ui and uj is equal to 0. They're orthogonal if I is not equal to j. So if you take any two distinct vectors from the set and look at their inner products, they'll be 0, meaning they're mutually orthogonal. And every single vector has norm 1. And this means the norm of ui is equal to 1 for all vectors I. And this is equivalent to saying that the inner product of ui with itself is equal to 1. Because if we recall the definition of norms, the norm squared is equal to the inner product with itself. The inner product with itself. So if the norm squared is equal to 1, or if the norm is equal to 1, the norm squared is equal to 1, meaning the inner product with itself is equal to 1. So the norm squared of ui is equal to the inner product with itself is equal to 1. And last thing to mention is that a square matrix with orthonormal columns, so if we have a matrix U with vectors u1 through un as its columns, all of which are orthonormal, so all of these vectors here are orthonormal, we call this matrix a unitary or sometimes orthonormal matrix. So orthonormal because all of its columns are orthonormal. In the standard linear algebra literature, you might see people refer to it as an orthogonal matrix, even though the columns are orthonormal. And we're just going to call them orthonormal matrices in this class, kind of to avoid any confusion. And unitary is just another way to say orthonormal, but in the complex case, and we'll actually see what it means to be unitary, like how unitary and orthonormal are different in some sense in a couple of weeks later. But for now, they're really the same because all of our matrices are going to be real. So any questions about orthogonality and unitary matrices? I think the last thing I also wanted to mention was that if a matrix has orthonormal columns, then U transpose U is equal to the identity. And this is because, like, if you just look at the transpose of all of the like U vectors in the U matrix, then you'll notice that the matrix multiplication is a bunch of inner products. And this means the diagonals will all be 1 because the vectors are orthonormal, and the off diagonals will all be 0 because they're orthogonal. And this tells us that U transpose is equal to U inverse if it's square. So any questions about orthogonality? I know some of this was reviewed from like 16A and Math 54, but all right. We don't have any questions. Let's move on to some new material now, specifically the spectral theorem, which now says if we're given a symmetric matrix A, we say that a matrix A is symmetric if A is equal to A transpose. So for example, if we have like 1, 2, 2, and 3, then if we took the transpose of this matrix, you'll notice that the rows or the columns become the rows and we'll have the same matrix. So this is what it means for a matrix to be symmetric. So given a symmetric matrix, all of these statements will be true. And first statement says that A has real eigenvalues. So sometimes we saw that we ran into complex eigenvalues for a symmetric matrix, or sorry, we ran into complex eigenvalues just for like an arbitrary state space matrix, which kind of led to oscillations and stuff like that. And if a matrix is symmetric, then, well, it has real eigenvalues no matter what. More importantly, we can say that A has n linearly independent eigenvectors, meaning A is always diagonalizable. So we can always write out A as V lambda V inverse. And the third statement tells us that the eigenvectors of A can be picked like such that the eigenvectors are orthonormal. So we can pick, another way to say this is we can pick orthonormal eigenvectors for the matrix A. And if we pick these eigenvectors to be orthonormal, then V will be an orthonormal matrix. And the significance of this is, well, V inverse is going to be equal to V transpose, as we said earlier over here. Meaning, we can write out A as V lambda V transpose, and this is going to help us a lot when it comes to just writing out the matrix in a more compact form. And this is also used a lot in proofs where if we know the matrix is symmetric, first thing we do is kind of just write out A is equal to V lambda V transpose by picking this orthonormal basis. So any questions about really anything we've talked about in the past couple of minutes, whether it was orthogonality or this new spectral theorem that we've brought up now? All right, if we don't have any questions about this, we shall move on to the discussion worksheet now. And we've basically talked about everything in the first page or so and started introducing the spectral theorem. And I think the last thing worth mentioning, are we going to prove the spectral theorem? I don't think we're actually going to prove it. I'll post a note. I think we have notes from the past where we have a full proof on the spectral theorem. You can prove it using induction. It's quite a difficult and tedious process, but definitely take a look at that if you're interested. And I think you can also like look up proofs online and yeah, take Math 110 for more details, honestly. Because I think the inductive proof is not the most intuitive. And anyway, moving on. We can, I think the last thing worth mentioning is that if A is written in the form B transpose B, then the eigenvalues of A are going to be non-negative. And this is something we're going to prove in the later half of discussion. So a lot of today's discussion is going to be on proofs, kind of just to get you warmed up to the SVD. The SVD kind of proving why the SVD works involves a lot of proofs as well. And we're going to use a lot of these facts that we prove in discussion today to do the SVD tomorrow. So in lectures. So we'll start with the first fact of the spectral theorem. So we're going to prove bits and pieces of the spectral theorem. We're not going to prove everything. I think the hardest thing to prove is really this last fact here, when we're not going to prove that. But we will prove that the eigenvalues are real. So I'll give everyone some time to work on this. And in the first part, we're asked to show that the eigenvalues of a real symmetric matrix are real. All right, let's start taking a look at this question now. So we're asked to show that the eigenvalues of a real symmetric matrix A are real. So whenever we do any of these proof kinds of questions, I think the best thing to do is always just to, for linear algebra proof specifically, just to write out as many definitions as you can and try to come up with as many definitions as you can and kind of puzzle the piece together. So we're going to start with a hint. Whenever you're given a hint, it's always good to start with the hint. And let's start by writing out AV is equal to lambda V. So we're going to start out by assuming V is an eigenvector of A with eigenvalue lambda. It's always good to kind of create a roadmap and think about what we need to show. So we want to show that lambda is equal to lambda conjugate. In other words, if the conjugate of lambda is equal to itself, then the eigenvalue lambda has to be real. So let's start by writing this out. AV equals lambda V. Let's take the conjugate and transpose of both sides. So if we take the conjugate of both sides, we're going to get A bar V bar is equal to lambda bar V bar. And the conjugate of a matrix is just taking the conjugate of every single entry. So as an example, if we have 1 plus j, 2 and 3 minus 2j, then the conjugate of A is going to be, it's going to be 1 minus j, 2 and 3 plus 2j. So we just take the complex conjugate of every single entry in the matrix. And since we're given that A is a real matrix, the conjugate of A is going to be equal to just A. The vectors aren't necessarily guaranteed to be real, so we can say that A V bar is equal to lambda bar V bar. And then the next thing the hint tells us to do is to transpose both sides. So if we take the transpose of both sides, then we're going to end up with V bar transpose, A transpose is equal to V bar transpose times, since lambda is a scalar, we can pull that out. And from here, might need to think about what to do now. And I think the next thing to think about is, what information were we given? Well, we were given that the matrix A was symmetric. So we know that A is symmetric, meaning A is equal to A transpose. So this tells us that V bar A is equal to lambda bar V transpose. Give myself a little more room here. And next thing to think about, we want to somehow show lambda is equal to lambda bar, and we're going to need to get rid of this A. So how do we get rid of this A? Well, let's try to right multiply by V.
I think there's a bar missing over the V transpose on the right-hand side.
Yeah. So if we right multiply by V, then AV is going to be equal to lambda V by definition, since we define it to be an eigenvector. So we get the following. And we can pull the lambda out. And from here, we can divide by V bar transpose V if V bar transpose V is not equal to 0. So any ideas? If you have any ideas, type them out in the chat on why V bar transpose V is not equal to 0. And I guess notice how if it is not equal to 0, then the two cancel and you have lambda is equal to lambda bar. But why would this quantity be non-zero? This is quite a difficult thing to show, but if we were to just treat v as a length n vector, then the conjugate of v would just be the conjugate of all of the individual entries. And this tells us that v bar transpose v, well, this is going to be the inner product of v with v bar, and we're just going to multiply the corresponding entries. So this is going to be v1 bar, v1, all the way up to vn bar, vn. And the claim that I'm going to make is v bar v is greater than 0. And it's greater than 0 because if you can write out v as a complex number, r e to the j theta, then v bar is going to be equal to r e to the minus j theta, where r is the magnitude, theta is the phase. This is just like the polar form of the complex number v. And this tells us that v bar, or v bar v, either way, is just going to be r squared. And these two, I guess, phases will cancel out. So since all of these terms here are greater than 0, this tells us that v bar transpose v is greater than 0. So since it's greater than 0, it's not equal to 0, so you can divide by both sides, and you're going to end up with lambda is equal to lambda bar. All right. Any questions about what we've done in this part?
Are we assuming the elements in V are not 0?
Yeah, so some of them could be 0, and this is a really good point. Someone also brought up in the previous discussion. The vector v, though, cannot be the 0 vector itself. And the reason it can't be the 0 vector is because it's an eigenvector of the matrix A. And eigenvectors, by definition, are non-zero.
Oh, okay. That makes sense.
And if you're unsure why, like, let's try to think about what it means. Like, if A times 0 is equal to lambda times 0, well, lambda can be any scalar, so it doesn't really make sense to define an eigenvalue for 0. That's kind of why we, by definition, say eigenvectors are non-zero. But really good point you bring up there that I almost forgot to mention. Okay, if we don't have any other questions, let's move on to the next part. Second part, it's kind of a baby proof for the spectral theorem, where we're now saying two eigenvectors corresponding to distinct eigenvalues of a symmetric matrix are orthogonal. So if we have v1 and v2 as eigenvectors with distinct eigenvalue, well, then v1 and v2 are orthogonal. And I'll give you some time to work on this one. All right, let's start looking at this part now. So first thing to do is always, if we're given a hint, let's try to use the hint. So we're going to start out by writing out the eigenvector eigenvalue equations. And the hint tells us to take the transpose of the second equation. So we're going to take the transpose of this equation, which we can write out as V2 transpose A transpose is equal to lambda 2 V2 transpose. Remember that if you have like AV, you take the transpose, this is equal to V transpose A transpose. Whenever you transpose the product of a bunch of matrix things, matrix vector stuff, got to always switch the order of multiplication. All right, and then we kind of got to think what to do. Well, we know A is symmetric. So since A is symmetric, we know that we can write this out as V2 transpose A is equal to lambda 2 V2 transpose. And from here, might be kind of stuck. Where do I go from here? Well, let's try to look at what we want to show. So we want to show that like the eigenvectors are orthogonal. In other words, we want to show that the inner product of V1 and V2, I'm just going to remove the vector hats because it got kind of annoying here, but I'm going to show that V1 transpose V2 is equal to 0. So we take a look at the expressions we have so far. We have a V1 and we have a V2. We want to somehow create this V1 transpose V2 term. So the way we're going to do that is to right multiply this by V1 so that we have this V2 transpose V1. And then let's try left multiplying this second equation, or this really first equation. Should be a lambda 1 by V2. So if we left multiply by V2, then we're going to end up with lambda 1 V2 transpose V1, because we left multiply this expression, lambda 1 V1 by V2 transpose. And these two quantities here are equal, meaning we can say that lambda 2 V2 transpose V1 is equal to lambda 1 V2 transpose V1. And by definition, V2 transpose V1 is just the inner product of V2 with V1. And then we know that these inner products are always symmetric, meaning the inner product of V2 and V1 is just the inner product of V1 and V2. And we're basically there. And now we got to show that this quantity here is equal to 0. And to do that, well, you can always just subtract this over. So lambda 2, the inner product, is equal to lambda 1, the inner product. You can distribute that out. Has to be equal to 0, because I've subtracted this term over to the left. And if the product of two things is equal to 0, then like V2 must be 0, or lambda 2 minus lambda 1 has to be 0. But we're given the fact that these eigenvalues are distinct. It's always good to go back and read the question one more time, meaning lambda 1 is not equal to lambda 2. So we know that this term is not equal to 0. And therefore, V1, the inner product of V1 and V2 has to be 0. And by definition, this tells us that V1 sometimes we use the sign to say orthogonal is orthogonal to V2. All right, any questions about part B? All right, if we don't have any questions about part B, let's move on to the next part. And the next part is going to be talking about that last statement we talked about, the one over here, where if we can write A as B transpose B, then all of the eigenvalues of A, or really the eigenvalues of B transpose B, are non-negative. So now we're asked to show the following for a matrix A. A transpose A is symmetric and has non-negative eigenvalues. And I'll give you some time to work this one out.
What does positive definite mean?
Yeah, positive definite, we kind of stated above over here, where the norm is always greater than or equal to 0. And it's equal to 0, like if and only if the vector itself is 0. So in other words, the norm of u is greater than 0 unless u is equal to 0, in which case the norm of u is equal to 0. So that's what it means to be positive definite. All right, let's start taking a look at this one now. And we're asked to show two things, so let's make sure we show both of them. First thing we're asked to show is A transpose A is symmetric. So I've got to show this. And just something I also want to note is that this matrix A doesn't have to be square. A transpose A has to be square, but A not necessarily is A doesn't need to be square. So to show this is symmetric, we can show that A transpose is equal to itself. Remember that that's what it means for a matrix to be symmetric. So if we remember the properties of transposes, you might recall that if you have the product of two matrices and you take the transpose, this is equal to B transpose times A transpose. So let's do the same thing here where we need to swap the order of the two. So we take the transpose of the second term, which is A, and then multiply it by the transpose of the first term, which is A transpose. And since the transpose of A transpose is just A, we've shown that A transpose transpose is equal to A transpose A. So that was the first part. And the second part is that the eigenvalues of A transpose A are greater than or equal to 0. In other words, they are non-negative. And to show this part, we can take the hint. Let's start by considering the norm of AV squared. Remember that by definition, the norm is equal to the inner product with itself, or the norm squared is equal to the inner product with itself. And the inner product here is going to be AV transpose times AV, which is then equal to V transpose A transpose AV. And from here, you need to think about what to do. And we want to show the eigenvalues of A are always greater than or equal to 0. So let's let V be an eigenvector of A with eigenvalue lambda. Or sorry, not A, of A transpose A. So if we let V be an eigenvector of A transpose A with eigenvalue lambda, this tells us that A transpose AV is equal to V transpose times lambda V. And this is equal to lambda times V transpose V, which is just lambda times the norm of V. And since the norm of AV squared is equal to lambda times the norm of V, this tells us that lambda is equal to the norm of AV squared. That lambda is equal to the norm of AV squared divided by the norm of V squared. And since norms are always positive, and we're squaring these values as well, you'll notice that the norm, or sorry, the eigenvalue lambda will always be greater than or equal to 0. And the norm of V is non-zero since V is an eigenvector of A transpose A. Remember how earlier we said eigenvectors can't be 0. So V is not equal to 0. So any questions about this part?
Wait, could you explain how you got the line right after where you wrote like let V be an eigenvector with the line?
So from here, I took this expression, V transpose AV, like this expression, and then I use the fact that like V is an eigenvector of A transpose A. So then A transpose AV is just lambda V, right? Is that what you were asking about, or are you asking about something else?
Oh yeah, I was just confused where the A transpose went.
Where the A transpose went? Oh, so V is an eigenvector of A transpose A.
Oh, okay.
Yeah, not A. I think I said A at the beginning, and then I corrected myself. But remember that A like doesn't have to be square, and if A is not a square matrix, it doesn't even have eigenvalues. Anyway, yeah. So we're always talking about the eigenvalues of A transpose A.
Okay, thank you.
Yeah, no problem. This fact, probably, yeah, parts B and C are the main takeaways, I think, for tomorrow's lecture. So tomorrow, when you're doing the SVD, we're gonna use these facts that like symmetric matrices have orthonormal eigenvectors for distinct eigenvalues, and this fact that like the eigenvalues will always be non-negative. So that's something to look forward to tomorrow in lecture. And let's move on to the last question now, which is on outer products. You might recall from lecture how we like wrote out a matrix A as a bunch of like sums of outer products. So we're going to spend some time today to develop more, I guess, the meaning of inner products and just take a look at more examples. kind of to help understand the SVD going forward. So the outer product is another way to multiply vectors. Remember how the inner product was one way to multiply them? But the outer product is kind of different because it takes two vectors and outputs a matrix, whereas the inner product gave a scalar. And I think we use this cross notation for the outer product, though I don't think we'll see much of it in this class. But the outer product is defined to be x times y transpose. So if x is a m by 1 and y is an n by 1, notice how the shapes can be different as well. We're going to have an m by 1 times a 1 by n, and we'll have an m by n matrix. So I think we can do these parts together, where part A asks us to compute the outer product of x, y transpose. So what we're going to do is we're going to just multiply these vectors and work out the matrix multiplication. And for me, I think the first time I saw this, it was kind of hard to understand like how to actually do the matrix multiplication. And you always got to remember, it's like, got to take the row and then multiply it by the individual columns. So what it's going to end up being is we're going to end up with 1 times 4, 1 times 4, 1 times minus 2, or sorry, 1 times positive 2. And then we're going to have 1 times minus 1. And then we can just keep doing the same thing. So this will be the outer product of x and y. I think another way to do this was kind of just to take this column vector, multiply it by 4, and that would be the first column. Then multiply it by 2, and that would be the second column, and so forth. What is the shape of A? Well, notice that if you have a 3 by 1 vector times a 1 by 3 vector, it's going to be a 3 by 3 matrix. And then last thing to notice, what is the rank of A? Well, we've taken this column, 1, 3, and minus 2, and we've just scaled it a bunch of times. So all of these columns are going to be linearly dependent. So the columns are all linearly dependent, meaning the rank of A is equal to 1. So this tells us that a single inner product, like x, y transpose, gives us a rank 1 matrix. I think you saw a lot of rank 1 matrices in lectures. So any questions about everything we've done so far in part A? All right. Let's quickly look at part B, since we're running out of time here, but the kind of intuition here should be that like the zeros don't provide any information, and we have this 1 vector over here. So in order to write this as a single outer product, we can take this single vector here, like all of these vectors here will be dependent. So we can take the vector 1, 1, and 1, and we can multiply it by a bunch of scalars. So notice how this first column, which is scaled by 1, and all of these other columns here would just zero out the vector. So this is how we would write B as an outer product of x and y. And the rank of B, again, will just be 1. But I think the more important thing I wanted to mention here was that when you have this inner product, or sorry, I keep saying inner product, this outer product here, like x, y transpose, this vector x is going to span the column space of A. So like 1, 1, 1 is a basis for the column space of B in this case. And that's because we're just scaling this vector 1, 1, 1 by like 1 and then 0 and then 0 and 0. So we're just taking this single vector and we're just scaling it as the columns of the matrix. So that's why the first vector of the outer product creates this basis for the column space of B. And for example, like if we were to have C equal to XY transpose plus UW transpose, where X and U are linearly independent, then X and U would, as a set, would form a basis for the column space of C. So, any questions about that specifically? I think the rest of the discussion worksheet, I definitely recommend you work out on your own time, and you're gonna get some like additional practice on the homework to do this as well. So,
So would C be then rank 2?
yeah, exactly. So C is rank 2. And this third matrix here, you can write as 3 inner products or 3 outer products, and that would be rank 3. And that kind of ties back to lecture where you wrote a rank n matrix as a bunch of like rank 1 matrices. And this is how we're going to build up the SVD. All right. It is past 12 o'clock, so it is officially the end of discussion. So thank you all for coming out today. But as always, if you have any additional questions about anything I've talked about on the worksheet, I'll be staying around for a minute or two. So feel free to ask any questions.